Hello everyone, my name is Tyler Breen, and today I'll be presenting my capstone project for cohort 2408. This project is a culmination of everything I've learned over the last 6 months in this bootcamp. I focused on AI and machine learning, and today I'm going to walk you through my process to develop an object detection model and navigate real-world accident data related to Tesla. I chose this project because I wanted to challenge myself and learn more about object detection. As a Tesla owner myself, I thought it would be an interesting opportunity to bring my own observations and experiences into the study. Object detection, in particular, is a fascinating area of machine learning, so I was eager to do this project. This project consists of two main parts. The first part involves creating the object detection model, and the second part, which we will discuss more later on in the presentation, focuses on studying accidents that resulted in fatalities involving Teslas. For part one, we were provided a dataset of over 110,000 images of random vehicles. The assignment asked that I develop an AI model using a deep learning framework, which predicts the type of vehicle present in an image as well as locates the vehicle using a rectangular bounding box. I'll walk you through that first part now. Before diving into the model, let me briefly explain what object detection is. In object detection, the goal is to teach an AI to recognize and locate specific objects in an image. It is different from regular image classification because we also need to predict where in the image the object is located. For my project, I trained the model to detect vehicles in images. My dataset included 110,000 images from security cameras, each containing multiple vehicles with corresponding bounding boxes that were marked where each vehicle is located. To begin the process, I loaded the dataset and faced my first challenge almost immediately. I quickly realized the limitations with my memory and processing power, since so many images take up a lot of space. To combat this, I decided to limit the training set to 1,000 images, with a distribution of 683 cars and 110 trucks and 61 other vehicle types. I then resized the images to 224 by 224 pixels so that they could be inputted by the model. After that, I split the images and the bounding boxes into training and test sets, with 80% going into training and 20% into testing. For the model itself, I was provided an architecture that contained convolutional layers, max pooling layers, and a dense layer. It's worth noting that this model is a hybrid. It both classifies the vehicle type and outputs the bounding box coordinates for the detected vehicle. I trained the model for 25 epochs, meaning it iterated over the dataset 25 times to optimize its weights and learn from the data. As you can see in the chart, the model's accuracy did improve during training, but it wasn't perfect. The classification accuracy score hovered around 60%, which indicated that the model still needed some work. While this wasn't the ideal result, it gave me a good starting point to refine the model further. Here is one of the model's predictions. The green box shows an actual location of a vehicle, and the red box shows where the model predicted a vehicle to be. As you can see, the red box does not correspond to a vehicle, but rather to a section of the road. Clearly, there were some errors in how the model was detecting vehicles, so I needed to dive deeper into the data to understand why. After some investigation, I realized that the bounding boxes aren't being resized properly when the images were resized. This was a key issue because the model was trying to detect objects in random parts of the image, rather than focusing on the vehicles. To fix this, I recalculated the resizing dimensions and adjusted the bounding boxes accordingly, which resulted in some improvements in the model's accuracy. But the biggest limiting factor I had was the limit of compute power and memory. Now let's move on to the second part of my project. Here I'm studying accidents involving Teslas, specifically fatal accidents, to understand trends and how Tesla's autopilot might be influencing road safety. I was provided with a data set of 300 accident cases, and my goal was to extract insights relating to Tesla's accidents. The first step was to inspect and clean the data. Some columns had missing values, so I removed those, and I also dropped a column that wasn't useful for my analysis. You can see in the first box the red representing missing values. Once the data was cleaned, I renamed the columns to follow Python standards, making it easier to work with. Next, I further pre-processed the data by extracting the year, month, and day from the date column to help with analysis. I also noticed that there was very little data from 2023, so I removed those entries from my analysis. I re-inspected the data with these changes and was pleased that the data was clean and pre-processed, as shown in the second box with the data represented in green. Here's a graph showing the number of accidents per year. I've also added data showing the increase in the number of Teslas on the road over time. What's interesting is that while the number of accidents and Teslas on the road has increased, the number of accidents per car has actually decreased, suggesting that Teslas may be becoming safer over time. This graph shows the number of accidents per month. Interestingly, there is a noticeable spike in November and December, which could be attributed to dangerous winter driving conditions. This suggests that weather plays a role in the frequency of Tesla accidents during certain months. This graph shows accidents by the day of the month. As you can see, there doesn't seem to be a significant pattern, meaning accidents are fairly evenly distributed throughout the month. Next, I looked at the geographic distribution of accidents. Looking at a global scale, we can see that the United States has the highest number of Tesla-related accidents, followed by China and Germany. This aligns with the global presence of Tesla and its adoption in these countries. Here we can see accidents per state in the US. California has the highest number of accidents, which makes sense given that it is a hub for electric vehicles and Tesla adoption. Florida also stands out with a relatively high number of accidents, which could be due to a mix of factors. So why does Florida have more accidents? It could be a combination of factors: a high number of Tesla owners, a large elderly population, and many out-of-state drivers who might not be accustomed to driving a Tesla. This raises an interesting question about the relationship between Tesla ownership demographics and accident frequency. Here are several graphs showing the number of deaths in Tesla-related accidents categorized. The first graph shows the number of people who died in each accident as a percent. The second shows whether or not the driver of the Tesla was killed in the vehicle. The third graph shows the number of passengers who died in each accident. The fourth graph shows the number of other vehicles involved in the accident. The fifth graph shows the number of pedestrians or cyclists that were hit. The final graph shows the total number of deaths in a passenger or cyclist accident, including the occupants of the Tesla. This tells us a lot about the nature of these accidents and the specific conditions in which they occur. This graph shows the distribution of accidents by Tesla model. The Model S and Model 3 are the most frequently involved in accidents. The Model S has been on the road the longest, so it makes sense that it would have the most accidents. But the Model 3 is also one of the most popular models, which explains its high number of accidents. Now, there is one more interesting piece of data to consider: the role of Tesla's autopilot in these accidents. This graph compares accidents caused by autopilot versus other reasons. As you can see, only 16 accidents were contributed to autopilot errors, compared to 275 accidents caused by other factors. Despite the media's focus on autopilot-related accidents, The data shows that autopilot is not typically the cause of fatal Tesla crashes. This could speak to the safety mechanisms built into Tesla's autopilot system. Next, I applied natural language processing to evaluate accident descriptions, aiming to categorize them into 6 types using unsupervised learning with the k-means algorithm. This helped me identify common patterns in Tesla-related accidents based on the language used in the reports. The 6 categories I identified were Teslas crashing into oncoming traffic, hitting trees, striking pedestrians, rear-ending stopped vehicles, driving off cliffs, and running over curbs or hitting poles. While this classification was useful for broad pattern recognition, it's important to note that it was not perfectly accurate. For example, if a report mentioned the word tree, it would likely fall under the hit the tree category, even if it wasn't entirely accurate. Despite its limitations, this approach provided valuable insight into the typical types of accidents involving Teslas. Here's a graph showing the distribution of accident types. The most common type of accident involved was Tesla killing pedestrians. This graph shows the number of deaths for each accident type. Cluster 3, which involves pedestrian deaths, is the deadliest accident type, while Cluster 1, which is related to rear-end collisions, is the least deadly. This breakdown provides valuable insight into the severity of different types of Tesla accidents. Here we can see how accident types are distributed across different months. Interestingly, Cluster 2 involving tree crashes shows spikes in May, September, and December. This could point to environmental or driving conditions that lead to specific accident types during those months. Thank you for listening to my presentation. I would like to express my gratitude to my instructor, Janet, for guiding me through this boot camp. I've learned so much, and I'm excited to continue exploring the world of AI and machine learning. I hope you found the insights from my project useful. Have a great day.